Okay, good afternoon, everyone. So thanks for the kind introduction. So it's my pleasure to present our work, TrustBoost, boosting trust among interoperable blockchains here. So this is a joint work with my collaborators, Payal, Kartik, and Pramod. So let's get started. So today we are living in a multi-chain world. So there are we all witnessed an expanding blockchain universe. So there are more than thousands of layer 1 blockchains. And today in the morning, I learned that by the end of this year, we'll have another 1,000 rollups. So there are more chains. But there do exist the security disparities among these blockchain ecosystems. So we have very strong blockchains like Ethereum and Bitcoin. They have very strong security, but we do have some weak blockchains with weak security, like those blockchains whose security relies on 5 out of 9 validators, to be honest. So those are less active blockchains, which means that they will also have higher vulnerability. So the question we would like to ask and answer in this work is that how can we make sure those less secure blockchains to become more secure? How can we boost the security of those weak blockchains? So we care about the security of any blockchain because of this cross-chain domino effect. So basically because in today's blockchain infrastructure, we have those cross-chain bridges over the blockchain interoperation between them. So this is one simple example, that is cross-chain exchange. Let's say Alice wants to move his Binance token to another blockchain, let's say Ethereum. Then the first step would be he would lock some Binance token in the Binance chain contract. And then the cross-chain bridge, basically some relayers, they will send some kind of proof that proves that Alice indeed has locked his token on the Binance blockchain. Then after this proof is verified, then someone will send a certain amount of each token to the Alice account on the Ethereum blockchain. But something can go wrong. What if there's a reorg attack happened on the Binance blockchain? Then basically in this example, Alice will get his ETH token for free. And this is a zero-sum game, so this means that someone in the world, somewhere, he lost some ETH token. So it's the real problem here is the security breaches can cascade through the blockchain network because of the cross-chain bridges. And typically, there are many ways to secure a weak blockchain. So a typical solution is called borrowing the trust. So this corresponds to some solutions like side chains and checkpoints. So basically, those chains will regularly submit checkpoints to a secure blockchain like Ethereum. But the problem of this approach is really that this is a one-way transfer of the trust from a strong blockchain to a weak blockchain. And most of the time, the weaker blockchains, they need to give up the individual sovereignty, which means that whenever there's some major change in the strong blockchain platform, those weaker blockchains need to adapt to them. So here in this work, we are trying to think about another approach. So we call it boosting the trust. So now today we have many blockchains. Can we simply boost the trust among themselves and just to generate a combined ledger that is secure than any of these participating ledgers? So we want two good properties. So the first one is we want the trust boosting to be adaptive. This means that the boosting can be offered simply via lightweight smart contracts. So it means that there's no need to launch a new blockchain or no need to change the consensus layer of those existing blockchains. And the second property we would like to is to have customizable trust boost. So this means that we can simply elevate the trust for certain high-value transactions. So if you have a very high-value transaction, then you should be willing to pay for it. So you just pay for the security. And this is our formal problem statement. It's here given M equally secure ledgers, but any of F of them can be 40. 40 means that they may not give proper safety or liveness guarantee. So given these conditions, can we generate a combined ledger? that this combined ledger is always safe and alive. And to make some notations here, we like to call these participating or constituent blockchains as local blockchains or local ledger. And the consensus they were using will be called local consensus. And this combined ledger will be called the TrustBoost ledger or the global ledger. So here, this problem actually has been started in a previous work called ledger combiners for fast settlement. They started the problem in a shared memory model. So basically, they model the blockchain clients as the processes, and the blockchains as some shared objects. And basically, everyone can read and write to those shared objects. Using the blockchain interface, they can submit transactions to those blockchains, and also they can check the confirmation state of the transaction. So, but the problem of this work is that they were not able to generate a total order ledger, so they did not solve the problem of consensus. So this can cause a lot of trouble, like you cannot implement a smart contract on this kind of ledger because they don't have total ordering of transactions. So that sounds like bad news. And in our work, we formally prove that as long as there is at least 140 ledger, then you cannot solve consensus in this setting. So this sounds like a really bad news. But the good news is that today the blockchains, they are pretty smart. So they are programmable. You can implement a smart contract on those blockchains. And they are also interoperable, meaning that they are usually connected by cross-chain bridges. So here we abstract the bridge as a cross-chain communication primitive. They allow the blockchains to send and receive messages from each other. So this, we call it the message in passing model. If you are familiar with some background in operation system, then there are two modes for two processes to communicate. One is the sharing memory, and another one is the message in passing. So here we would like to combine these two approaches. So we will use two primitives to construct this combined ledger. The first primitive, as I just introduced, is the cross-chain communication protocol, and this can be instantiated by some real-world project like the IBC protocol in Cosmos, or XCM in Polkadot, or the CCIP protocol, which introduced by Chainlink, which is a general bridge protocol among any heterogeneous blockchains. And another primitive we like to use is the local consensus of those local underlying ledgers. So we assume that they use some kind of consensus to maintain safety or liveness. So this can be any type of consensus, including like PBFT style protocols, like Tendermint or Hotstuff, or it can be like longest chain or Nakamoto style protocols like Ouroboros. So with these two primitives, we are ready to build our TrustBoost ledger. So I will give you one example to show how TrustBoost works. So basically, it's implemented in a lightweight way using smart contracts. So here we will use the example of name service, and we would like to upgrade this smart contract into a cross-chain version. So here we name it name service X. So basically, name service is a very simple contract with only a few lines that allows you to register a domain name on a blockchain. And on the left-hand side of these lines, you can see like this is normally how name service contract works in a blockchain like Ethereum. So there are submit and check interface provided to the client. And the client can simply submit a transaction saying that I want to register a name ABC. Then after this transaction is committed on the blockchain, then he got the domain name. And on the right-hand side, we have a construction for TrustBoost. So from the client's perspective, it looks exactly the same as a normal ledger. So it has the same interface, submit and check. But inside the box of TrustBoost, we have here we have M underlying local ledgers. And on each of these ledgers, and they are connected by a cross-chain communication layer, and allow them to send and receive messages among each other. And on the top of each of the ledger, we deploy the two set of contract The first one is the application contract. In this example, is the name service X, and basically it's the cross-chain version of the name service contract. And it turns out that we only need to change a few lines of code in the original contract. And another contract, which is our main contribution, is called the TrustBoost contract. So it basically implements the logic of a full consensus protocol, but using smart contract. So for example, we can use a leader-based consensus protocol like Tendermint or Hot Stuff. So then in this example here, this will, if the client then again he wants to submit a request saying that I want to register ABC, then first this request will be sent to a leader blockchain, leader ledger, and then after complicated consensus protocol, the same transaction or the same request will be replicated on all these underlying ledgers, but using the consensus protocol implemented in the TrustBoost smart contract. And about the security analysis, it's actually very straightforward because we can simply reuse the security analysis of the consensus protocol we implemented in TrustBoost. So we simply model the blockchain as objects. If the blockchain has some super majority honest assumption, then it simply behaves as a non-faulty object or non-faulty validator who will not equivocate, who will follow our protocol. But if it does not have the super majority security guarantee, then we allow the blockchain to behave arbitrarily. So basically, it can be modeled as a Byzantine node or Byzantine validator. And here, the CCC, we simply model it as an authenticated channel. And if the underlying ledger, if they can provide a certain type of proof of commitment, like the quorum certificate that is generated by Hot Stuff, then we can simply use this as a signature among the blockchains. And even if they do not provide such a signature, it's still possible to use the light clients to check the states, check what happens on the other blockchain. And actually, my talk can stop here, and our paper can also end here. It's like a fine paper, but we do want to have some practical and immediate relevant. So we found that actually Cosmos, they have this Cosmos SDK, which implements Tendermint as local consensus, and it's very easy to use. Anyone can set up their own Cosmos blockchain within 10 minutes. And they also provide this CCC primitive, that is the IBC protocol, that connects these blockchains. So basically, Cosmos ecosystem is the internet of blockchains and provides the ideal environment for us to implement the TrustBoost. I guess I will skip some technical details in our implementation, but if you are engineering in the blockchain space, you should understand that implementing a consensus protocol was never easy, and not to say that we implemented in smart contracts. So there are quite a few limitations when implementing that in smart contract, including like single-threaded, but we were able to fix that. For that, feel free to read our paper and to check out the details. And the consensus protocol we implemented in TrustBoost is called information theoretic hot stuff, which was the state-of-the-art BFT protocols without using any public key. And actually later this protocol is still like fairly complicated. So lately I worked a little bit on this field. So we were able to improve this protocol a little bit. We can reduce the communication complexity by a round of 1. So that's my recent work with my student. And after implementing TrustBoost, we also did some evaluation on the protocol. So basically, we care about the 2 questions. The first one is, what is the price the user need to pay for the security? Like if they want to move their application to the TrustBoost ledger, if they want to buy a higher security, what's the price? And the second question we would like to answer in the evaluation is that how well does TrustBoost scale, like in the number of underlying ledgers? So this table shows the results. So basically, you can see that the gas usage of TrustBoost scales actually correctly in the number of nodes, but that's kind of expected because the consensus protocol we implemented is has a quadratic communication complexity, and the latency also scales linearly. And although here, like when we have 10 underlying ledgers, the total gas usage is about 600 million. That looks like a lot, but actually it turns out it only costs about $2 to $10, so which is kind of compatible or in line with the cost on Bitcoin or Ethereum blockchain. So those are very strong blockchains. And we also were able to identify some approaches to further reduce our gas usage. So the first one is that we can try batching and to amortize the gas cost for the TrustBoost protocol. And another one is that we should really try hard to improve the IBC efficiency. Like here currently, the IBC protocol, even for one cross-chain token transfer, could cost about 2 seconds and 350,000 of gas. So, but if we can reduce these numbers, then the performance of TrustBoost can be improved significantly. Okay, and I would also like to show some use case of TrustBoost. So the first application is about the checkpointing service. So right now, many blockchains, they decided to checkpoint to Ethereum or Bitcoin because they believe that Ethereum Bitcoin has very strong security. But here, we provide another way to do checkpoint because now we can construct a strong ledger just out of these weak ledgers themselves. Then we can use this TrustBoost ledger and to checkpoint all those ledgers. And then we just need to slightly change the finality rule of this ledger to follow the checkpoints. Then in this way, all those underlying ledgers will share the same security level as this TrustBoost ledger. And another application is for cross-chain token transfer, like the attack or the vulnerability I showed at the beginning of my talk. Like now, if you want to have a really high value transaction or your token is really valuable, then it's possible for you to move the token stake to the TrustBoost ledger. And here the guarantee is that your state will share the same security level as the TrustBoost ledger, and only the token state need to be upgraded. But all the other applications, you don't want a strong security, can still reside on the underlying local blockchains. So although this paper is kind of new, we presented this paper at CCS 2023 last November, but there are already quite a few follow-up works by my collaborator or some other blockchain researchers. So I would like to say this is a new research direction that is called smart contract executable distributed protocols. So there are quite a few follow-up works, including one paper already accepted by CCS 2023, and quite a few new papers also in this direction. So basically, they implemented a distributed protocol using smart contracts. Some protocols are fairly simple, like just some timestamping protocols, or some protocols are even more complicated than the consensus protocol we implemented in TrustBoost. Okay, so as a conclusion, so here, in TrustBoost, we provide a way to boost the trust among a group of weak blockchains, and we started this trust boosting problem in an extended model fitting today's multi-chain framework in our blockchain infrastructure. And one way to understand TrustBoost is that TrustBoost is simply a proxy smart contract to improve the application security. And we also identified quite a few future directions, like here we assume that every blockchain have an equal amount of security, but actually we can also implement unequal ways of boosting, like we can measure the security of a blockchain by the market capacity of that blockchain. So that should be very straightforward. And also some other future directions, like to improve the efficiency of the CCC or to improve the efficiency of the underlying consensus protocol. In both ways, we will be able to improve the efficiency of TrustBoost. Okay, so that concludes my talk. I would like to thank you everyone for your time. So here are a barcode for our paper and my email address. And you can also find the full paper here through this link. And a little bit for myself, I'm a faculty member at Hong Kong University and Guangzhou, and I'm also a consultant at School. So so both my research group and the School protocol team are still hiring. So if you have students or if you want to work with exciting problems, so feel free to reach me.